Hi there, I'm Professor Ivory. Ever wonder how AI models like ChatGPT can write stories, answer complex questions, or even generate code, seemingly pulling information out of thin air and doing it so quickly? Magic lies in something called the transformer architecture, and specifically, its attention mechanism. It allows the AI to weigh the importance of different words when generating the next word. But there's a hidden challenge. Generating text one word or token at a time means that for every single new token, the model traditionally had to reprocess all the previous tokens. Imagine reading an entire book from the beginning every time you wanted to add just one more word. Inefficient, right? That's where a clever trick comes in, the KV cache. It's a cornerstone of making large language models fast and efficient. Today, we'll break down what the KV cache is, why it's crucial, and how different attention mechanisms like multi-head, multi-query, and grouped query attention interact with it to strike a balance between performance and power. Stick around, because understanding this is key to understanding modern generative AI. Okay, quick foundation. Transformers that we mentioned earlier use something called self-attention. Think of it like this. For every word or token the model is considering, it generates 3 vectors. Query, Q, what am I looking for? A key, K, what information do I hold? And a value, V, what information do I offer? The query of the current token checks against the keys of all previous tokens, including itself, to see how relevant they are. This creates attention scores. These scores then decide how much of each token's value gets blended into the representation for the next token. This lets the model pay attention to the right context. But remember our problem? When generating the 100th word, we need the keys and values for words 1 through 99. When generating the 101st word, we still need the keys and values for words 1 through 100. Calculating these K and V vectors over and over again is computationally expensive. This is where the KV cache saves the day. The idea is simple but powerful. Don't repeat yourself. Once the key and value vectors for a token are computed, we store them in this cache, a dedicated spot in the model's memory, usually the GPU's VRAM. Now, when generating the next token, say token T+1, we only compute the new Q, K, and V for that token. Then, we simply retrieve the already calculated Ks and Vs for all the previous tokens, 1 to T, directly from the cache. We perform the attention calculation using the new query against all the keys, the new one plus the cached ones, and combine the values. The result? A massive speed-up during generation called inference. We avoid tons of redundant calculations. It's like taking notes in a meeting. Instead of replaying the whole recording, you just check your notes. Now, basic attention is good, but transformers usually employ multi-head attention, MHA. Imagine having multiple attention mechanisms, or heads, working in parallel. Each head learns to focus on different types of relationships or information in the text. Maybe one head focuses on grammatical structure, another on semantic meaning. This is powerful, but it impacts our KV cache. With MHA, each head calculates its own key value vectors. So, if you have, say, 12 heads, you need to store 12 separate sets of key value vectors in the cache for every single token. For models with many heads, some have 96 or more, and long sequences, thousands of tokens. This KV cache can become huge. It eats up precious GPU memory, limiting the size of models we can run, or the length of text we can process efficiently. This became a new bottleneck. So how do we keep the benefits of multiple perspectives, query heads, without the massive memory cost? Enter multi-query attention, MQA. The clever idea here is to still have multiple query heads, each learning different key projections, but make them share just one set of key and value projections. Think of it like a panel of experts, the query heads asking different questions, but all referencing the same shared library of information, the single key and value vectors per token. What does this do to our KV cache? It shrinks dramatically. We only need to store 1K MV vector per token in the cache, shared across all query heads. The cache size is reduced by a factor equal to the number of heads. This means significant savings in GPU memory and the bandwidth needed to read-write to the cache, leading to faster inference, especially for long sequences. It allows us to run larger models or handle much longer contexts on the same hardware. There's a small potential trade-off in model quality, but MQA has proven incredibly effective in practice. MQA was a huge step, but as sharing only 1 KV set may be too restrictive, Grouped Query Attention, or GQA, offers a middle ground. Instead of having 1 KV set, like MQA, or as many KV sets as query heads, like MHA, we use a few groups. Let's say we have 12 query heads. We could group them into perhaps 4 groups. All heads within a group share the same KV projections, but different groups have different ones. It's like splitting our expert panel into smaller committees. Each committee shares its own internal library of documents, their KV set, which is different from the libraries used by other committees. A KV cache size for GQA sits between MQA and MHA. We store K and V vectors for each group. Equa aims for the best of both worlds, significantly reducing the memory footprint compared to MHA, while potentially offering better quality and expressiveness than MQA by allowing more diversity in the keys and values. Many recent high-performing models, like Llama, use GQA, so why should you care about all this? The KV cache and optimizations like MQA and GQA are fundamental to making today's powerful AI models practical. Speed, the cache makes generation fast and responsive. Memory efficiency. MQA/GQA allow huge models to run on available hardware and enable much longer context windows, meaning AI can understand and generate text based on more preceding information, leading to better coherence and capabilities like summarizing long documents. Accessibility, efficiency improvements make these powerful tools more accessible to more people and researchers. These aren't just abstract concepts. They directly impact the AI tools you use every day. They represent the clever engineering needed to turn theoretical possibilities into real-world magic. To recap, self-attention needs past keys and values. The KV cache stores them to avoid recomputation, speeding up generation. Multi-head attention increases cache size significantly. Multi-query and grouped query attention drastically reduce cache size by sharing keys and values among query heads, enabling larger models and longer contexts. Hopefully, you now have a clearer picture of the KV cache and its vital role alongside different attention strategies in generative AI. It's a fantastic example of optimizing performance where it counts. If you found this helpful, please give the video a thumbs up, subscribe for more deep dives into AI, and let me know in the comments if you have any questions. Thanks for watching.